Hey guys, my name's Zach. Some of you may already know me, but anyways, I am going to go over some basic CAD training for FRC Team 7886, and let's get started. This is part 1 of a decently long series, I hope, but here goes. So let's just start with the basics. What is CAD? CAD stands for Computer-Aided Design, and it's the use of computers in software to aid the creation, modification, analysis, or optimization of a design. These images, as shown here, are drawn in CAD, and the program produces them using vector-based graphics, and you can often include construction materials, processes, dimensions, tolerances, and much more within your drawings. So it's not just a simple representation. If you look here at this pipe, you can represent what material it is, so when you go into the simulation parts of most CAD programs, it will be able to tell you how much stress that part can endure and how it's going to act in a very simplistic manner. You can't do super complex simulations in CAD, but for simple things like tension, or like if you're modeling something colliding, it will do. Alright, next, some very common CAD software, especially in FRC robotics. We use Fusion 360, AutoCAD, SolidWorks, Onshape, or Google SketchUp. Google SketchUp is the simplest of the bunch. It's free, but it's essentially like a Google Docs compared to your Microsoft Word. So most teams don't use that because it's limited in its features. The software you see highlighted in blue are the more common ones, and most of them are sponsored by FRC. So that means that if you register as a team and you get the basic kit of parts, you can apply for a free license. Normally, these software will cost you a lot of money. Fusion 360 is in like the $400 range per year, but for students, it's free. So I've included links in this slideshow because I will share it. And if you want to download any one of these, you can just click on it, just fill out some forms once you registered under a first team, and you'll be able to access these programs for free. Now, I personally use Fusion 360, but Onshape is a very good, completely cloud-based option. So, all of these software, excluding Onshape, you will have to download onto your computer as an actual executable file. What Onshape does differently is it's basically a completely web-based program, so you don't have to download anything, and it allows for easier collaboration. So, I use Fusion 360, but we might switch to Onshape simply because it will be easier to collaborate. Alright, so before we get started into teaching the basics of CAD, I'd like to talk about how CAD fits into the design process. So I will create an engineering slideshow for a mechanical team, but for now it's unlinked. I will link it later. But let's get started with advanced teams. So for advanced teams, they have a lot more resources, a lot more experience, and typically they get started over the summer or do a lot of off-season training. So what this allows them to do is move CAD much earlier into the design process and create much more complex machinery. So I'll break that down in a bit, but basically this is a simplified version of your design process. You want to analyze and break down that year's problem. So you'll go into the rulebook, you want to read it very carefully because there will often be little parts of the playing field that help advanced teams that completely go through the game manual to take an advantage over the teams that don't fully understand the game manual. So I'll just give you an example because that's kind of harder to understand. Last year, our game was to basically take dodgeballs and shoot them into towers, right? And the field looked a little something like this. Right, so now if you'll notice, if you're on the blue team, right, you want to score in this tower, but your driver station's over here. And this is where you can give your robot all of the balls, provided you've scored everything on the actual field. So, the quickest way to make it from here, the loading station, to here where you can score, was through the trench. A lot of teams didn't fully read the game manual, so they didn't know that, and they built robots that were too tall to fit under the trench. And that wasted a lot of valuable time and allowed the teams that actually did read the game manual to hold an advantage over the teams that didn't. So that's just a basic example. I wanted to bring that up because this happens a lot. Anyways, you break down and you analyze the problems, and what you want to do from there is you want to decide, okay, so what are our objectives and what parts of the robot do we need to complete those objectives, right? So last year, let's go back again. You wanted to somehow pick up these dodgeballs or load them from the driver's station and shoot them into the ports to score points, right? There were two other mechanics of the game, which were climbing at the end on these hangers and spinning the color wheel after you scored a certain amount of points. So what that basically meant was that you had to have a drivetrain, obviously, to move your robot around. You had to have an intake that could either pick up balls directly from the field on the ground or from your driver's station. You had to have something to climb. You had to have something to spin the color wheel, and you had to have a shooter. And if you were trying to be efficient, you would obviously also have a storage for the dodgeballs because you were allowed to store up to 5 at once, and it's much quicker to pick up 5 at once, shoot them all out, instead of doing it one by one. Right? This is something we call run time, so how long it takes you to complete a full cycle of what you want to do within the field. Right? So you take the problem, you break it down, and then you transform that problem into the components necessary to complete that game, that year's game, right? And once you've done that, you can start brainstorming how exactly you want to design those components. So what's your shooter going to look like, how you're going to store the balls, what mechanisms will you use, right? And now for advanced teams, they have a lot of experience, so they don't really do this, especially the top teams. They just they're able to design these designs themselves. But for smaller teams, I'll skip to the beginner team slide really quick. I want to emphasize this point. There's no need to reinvent the wheel, alright? So I'll give a quick example here. Last year's game, as I already explained, you needed to shoot dodgeballs into a port. What that basically means is that you need a shooter hood. And it just so happens that FTC, which is a junior competition of FRC, had a game that involved shooting softball-sized balls into a funnel. And so what a lot of teams in the mid-range did was that they just straight up looked at the designs from FTC, made some modifications to improve the shooting power because our balls were bigger, and to increase some accuracy because they wanted to shoot from farther, as well as increase the size because the balls were bigger. Right, so if you looked at the FTC shooter designs, a lot of teams just looked at these and based their design off of this. There was no need to completely start from scratch. They just based their designs on what was already out there. Alright, so for a lot of newer teams, this is the best option. It might not seem that creative and you might want to do it on your own, but trust me, if you don't have that much experience, your designs 9 times out of 10 will not work the way you want them to, and then you'll end up wasting a lot of time. So once you have decided on designs, whether you take them from other teams or you come up with a novel idea on your own, you want to prototype, and then advanced teams, they'll use wood or Vex aluminum bar kits, stuff like that. It's very easily modifiable, where you can repurpose the same materials for other things, right? If you look at the Vex aluminum bar kits, you'll notice that they have holes on them, spaced every other inch, or in some cases even closer than that. And what this allows them to do is basically change the dimensions of their framing as needed. It won't be perfect, but it will be close enough. Alright? So you want to use these kind of materials to prototype, and then once the advanced teams finish prototyping, they'll just CAD their entire robot. I do not personally recommend this practice because a lot of things can go wrong. It might look good on CAD, but it might not work out on in actual practice. But they'll just CAD the entire robot, mechanical and electrical. So electrical CAD is ECAD. That's just what it stands for, and it basically allows you to model all of your hardware and all of your wiring. In I guess it's kind of 2D instead of 3D, but it's the same thing as CAD, just electrical components. Right, so they'll model the entire thing, and then a lot of teams, what they'll do, since the stuff they model will not be based on what is provided in the kit of parts. I'll explain more on that later, but all their parts are customized. So if you take a look at the Robonauts, you'll look and you'll find that all of their robots have custom cut out parts. And how they do this is they'll design the parts in CAD, and those files can be downloaded as STL or other types of 3D files, converted into G-code for CNC mills and 3D printers, and they'll just manufacture those parts on site. Let's go back. If you look at the framing for the Robonauts, you'll notice that there's a lot of custom structures, and a lot of these structures have these geometric shapes cut out of them. That is something called lightning that I will explain in the engineering slideshow, but that stuff is all cut using CNC mills. Normal beginner teams do not have the money or capabilities to do this kind of stuff, so this doesn't really apply to beginner teams. I want to emphasize this because, like, there's really no point for beginner teams to CAD all of their stuff before they actually have an assembled robot. Alright, so as mentioned in the slides, the benefits is that you get custom parts fit your exact requirements, but the cons is that it requires expensive machinery and a lot of experiences, both of which beginner teams like us cannot afford. So once they have everything CAD'ed, everything converted into actual physical hardware and mechanical pieces, they'll just assemble a robot. For them, it's essentially like building a Lego kit. Everything is already pre-designed, you just assemble it. It's a lot easier, and then once they do that, they will test, as you should. Test, make final adjustments. Sometimes they'll have to redo their CAD and reprint and re-carve out specific parts, which is why I don't recommend this practice for beginner teams. But most of the time, like the very advanced teams, they will get like significantly most of their robot right, so they won't have to do a lot of adjustments, but they still will make final adjustments before actually competing with their robot. Now, I already mentioned a lot of this slide while talking about the advanced slide, but let's just go over it one more time. So beginner teams, as always, analyze and break down the problems, convert it into whatever components you think the robot might need. You brainstorm and look at designs from previous years. There's, once again, no need to reinvent the wheel. If you do have a really good idea, you want to prototype that idea as soon as possible, right? You want to prototype everything, but if you have a really good idea that you haven't seen other teams do, that you can't like take from what they've done, you want to prototype as soon as possible. For beginner teams, this will mostly be done using wood, so like motors will be replaced by electric hand drills, stuff like that. And modular testing, alright, this is important. So this is a term used a lot in, I guess, code development and software development, but I think it applies nonetheless to robotics because, like, one, robots do involve code, and two, your robot will be modular if you've done everything right. So modular testing, what I basically mean by this, I might be using this term wrong, but if you build an elevator prototype, you can reuse a lot of those parts. Okay, actually, let me start from the beginning again. Modular testing, you want to test every component of the robot separately. You can use stuff to help you emulate the robot and how the actual component will fit into the final robot, but you want to test everything separately. And what you can do in modular testing is that in an elevator, let's say an elevator, it will usually have frames, so that's aluminum bars, sprockets, chains, motors, some nuts and bolts, stuff like that. Right? That comprises an elevator, but if you're running low on budget and you're a new team, you can reuse a lot of those parts in your shooter, in your intake, in your drivetrain. Not your drivetrain. Your drivetrain you want to keep intact, actually. Strike that. But you can reuse it in a lot of the other parts of your robot when you're doing prototyping. So modular testing not only helps you isolate the problems, it also helps you conserve resources. Alright, to recap, you want to use modular testing because it allows you to isolate problems within each component itself, saves materials, saves money, saves some time, because honestly, if you integrate everything into a robot, even if you do it all out of wood, if you have a problem, it's going to take forever to identify where it comes from. So modular testing just makes things a lot easier. And if you want to CAD at this stage, for beginner teams, I would suggest you use sketches. So you create 2D blueprints where you simplify a lot of things. So let's say an intake from last year, the intake would be able to go up and down like this to pick up the balls, right? You can model that simply by using a straight line that rotates around a center pivot point. We'll go more into depth on this later, but for now, just know that if you want a CAD here, which I do kind of recommend, you don't want a full-blown CAD, you can use sketching and make simplifications and create a rough sketch, but you want to include dimensions in this if you do, of the robot, and it allows you to see if some things really just don't work out because of the dimensions clash, stuff like that. And once you're done with prototyping, you build your prototypes using the final materials. So you swap out everything wood for aluminum bars, parts from HandyMark, parts from Vex, parts from other companies. And after you assemble the whole robot, you want to test, test, and test. Extensive testing, because nothing will probably work the way you want it to. If you're lucky, it might, but there is always room for optimization. Alright, so as you test, you make you make adjustments, you make revisions, you go back. Sometimes you have to redesign the entire part because it just doesn't work the way you want it to. And then you test, test, test again. And if you finish on time, or even beforehand, and you feel like some parts can be optimized cheaply and efficiently using custom parts, then I would suggest to CAD. So our school has a large wood CNC router, which could serve in this situation. But again, you only want to CAD and create custom parts if you feel like it can be like a certain component can be optimized cheaply and efficiently. Alternatively, CAD is really just icing on top of the cake, so we CAD'd last year after the robot was finished, just to give it a more whole presentation look. And yeah, icing on top of a cake, like I said. So I wanted to do a quick little case study about why everything I just said really is important. So this right here is our robot from last year. At our very first competition, there were a lot of things wrong with it because we didn't have enough time to test. Alright, and over here, this is the CAD file I created of our robot during the summer after the season ended. Obviously, this robot would have been modified had our season continued, but it was cut short by Corona, and this is what I think a better version could be, potentially. Obviously, it's not tested again, so you never know. I am not a professional engineer by any means. Alright, so let's just quickly run over our robot from last year. So, immediately, you'll notice a couple of things that are, not to say wrong, but could be a lot better. So, wires all over the place. Wire management last year was a disaster. Okay, you don't want wires in anywhere near the vicinity of moving parts. So this, near the motor and sprockets and chains, are dangerous. This, potentially dangerous. Alright, so you want to keep wires as close to whatever frame structure it's attached to as possible, maybe even inside or within tubing and away from moving parts. Alright, so that is more electrical, but anyways, that is something wrong. Another thing you'll notice is that a lot of our chains are exposed. That's not necessarily a problem, but it could be dangerous in collisions. Same thing down here. And now let's talk about the components, alright? So the intake. Intake last year was alright, but there's a distinction between the intake I drew here and the intake that we actually used on the robot, which is the chain guard. Alright, so last year we put a chain guard made out of an aluminum sheet that was just bended to roughly cover the chains, and that surface area was too big and it was a little too flimsy. So what it essentially did was provided a surface for the ball to roll under, and since there was nothing there except maybe the chains that could have touched the balls either got ripped or pushed under a robot, which could have caused tipping Thank God it didn't, but it could have, and most of the time, even though the robot didn't hit, it still got stuck and wasted valuable time. Right? You also notice that it's not shown in this picture, but last year we did try to use Omni wheels. These things are, no, Mecanum wheels. These things are called Mecanum wheels. And what it essentially allows you to do is if you spin it in a direction, it allows translation in a direction that is perpendicular to the spinning. Alright, so it spins forward, the ball moves left and right. So while we had Mecanum wheels on our intake last year, which would allow any ball around this vicinity to go towards the center and be pulled in by the actual spinning wheels, the Mecanum wheels were a little too small, so they didn't have that much power in pushing left or right, and it really just served the purpose of shoving balls under our robot, which caused jams and stuff. So that was an issue, and now the component I wanted to go over is the shooting hood. Alright, you might be noticing a common theme here. We ran out of time, and the shooting hood, if you look, this is the shooting wheel, right, and then you'll notice that it matches the Cad. But what doesn't match the Cad is the shooting hood. You'll notice that this shooting hood is oriented on the same side as the shooting wheel. Now, the purpose of a shooting hood is to guide and compress the ball. The ball needs compression to travel far, right? Otherwise, if you don't compress the ball, it's just going to roll up and out of the shooter. If you have the flywheel fast enough, it might go some distance like ours did. But essentially what it did was limit our robot's shooting range to like 3 feet, which meant that our robot did not have a lot of versatility, and so this shooting hood was basically useless, so we will try to replace it with this one this year. Now let's get started with the actual CAD tutorial. I use Fusion 360, and as you can see, you might have saw on the slide there, sketching is your best friend. So this is our robot from last year in its full flesh. There is a problem with Fusion 360 in which if you load parts from other sketches, so if you don't create rigid joints, the parts might get dismembered during the importation process. So that is no good, but if you saw in the slideshow, this did not happen beforehand. And alright, this is our robot. I'll do a quick orbit around just so you can see. It's not the prettiest, but I take pride in it. And this is just what a CAD file kind of looks like while you're designing.